So last talk of the conference, I'll keep it short, right? So today I'm going to talk about how simple testing or embarrassingly simple testing can be used to prevent the most critical failures. And this is a collaboration with my students and my colleague. And in this work, we have manually analyzed hundreds of real-world user-reported failures to some high-profile distributed systems. And in my talk, I'm going to focus on three key findings, right? First, we found that these failures are often the result of complex sequence of events. But if you look at the most catastrophic ones, they're almost entirely caused by incorrect error handling. And surprisingly, many of these bugs in the error handling code are extremely trivial, that they simply violate a few programming rules. And we built a simple tool. It's a static checker called Aspirator that can successfully find hundreds of real-world bugs. And so over 100 of them are already confirmed and fixed in these systems. All right. So we know that distributed system failures can be deadly. In 2011, there was this failures in Amazon AWS that took down Reddit, Quora, Foursquare, Instagram, Netflix, and 70 other sites, and probably including some of your websites. Right? It lasted 4 days. Okay? And in 2013, Google went down briefly for 5 minutes, and the internet traffic plunged by 40%. And last year, Facebook went down for 30 minutes, and some users called 911. Then the question is, why do these systems fail? Okay? To answer this question, we conducted a manual study on the failures. In particular, for each failure we study, we thoroughly analyze its entirely failure propagation sequence. By that, we mean that usually a failure, when it occurs, there is a fault, which is a root cause. It can be a software bug. It can be a hardware fault. It can be a user misconfiguration. And once the fault is triggered at runtime, it will manifest into an error where the system starts to misbehave, such as exception being thrown or a system call return error. Okay? And if it's not properly handled, it will eventually manifest into a failure, which is user visible. And now, by understanding this entire life sequence of the failure, it allows us to identify the minimum condition to expose the failures. And also, perhaps more important, it allows us to understand what is the weakest link connecting this chain so that we can break it and prevent these failures from happening. And in research, it's all about novelty. We are not the first one to study failures, but none of the previous work have looked at this entire failure propagation chain. Okay. Now, to drive our study, we have sampled 198 user-reported failures to these 5 distributed systems. They are Cassandra, HBase, HDFS, Hadoop MapReduce, and Redis. And for each failure, we carefully studied the discussion between the user and the developers and the related code and patch. And we ended up replicating 73 of them, just so we could understand them. Okay. But not every failure has the same criticality. Okay. So among these 198 failures, 48 of them are catastrophic. By that, we mean that these failures will affect all or a majority of the users. So for example, if there's a failure to take down one node, it's not catastrophic. Or one user cannot access its data, it's not catastrophic. We only consider a failure to be catastrophic if all the nodes are down or all the users cannot access their data. And we studied this set of failures specifically because they are the ones that cause people to lose their job. Right. And now we are going to dive into our findings. Okay? First, I'll explain that these failures are complex. But for the catastrophic ones, they're almost entirely caused by incorrect error handling, and many of them are surprisingly trivial, and how we build a static checker to detect many of these bugs. All right, I'm going to use one real-world failure example to make a few observations. And this failure example is from HBase, which is a distributed NoSQL database. All right? It has a master and slave architecture where each slave is responsible to serve some user data. So the user data in HBase is called a region. Okay? Now, in this case, a user reported there's a sudden outage to the entire HBase cluster, so it's a catastrophic failure. I'm also showing the code snippet that contains the actual root cause. Now, in order for this failure to occur, a few events need to happen. All right? First, there needs to be a load balancing event where a region is transferred from a slave to another more idle slave. And once this event happens, as a consequence, this slave B will try to first open this region. Okay? And once it opens the region, it will tell the master that the region has been opened, and the master will try to delete a zookeeper node, which is used to indicate that this region is being opened. Now, if right after this zookeeper node is deleted, node B crashes, then in this case, the master will try to handle it by selecting another slave and try to open this region. And now slave C is assigned to open this region, and it will trigger the same logic. It will first open this region, and once it's opened the region, it will tell the master the region is opened, and it will trigger the same code snippet. Now, in this case, the master will try to delete the zookeeper node again, but this time it will throw an exception, because this zookeeper node has already been deleted. But unfortunately, this exception is not properly handled. So in the handling of this exception, it simply takes down the entire cluster. Right? So as a result, to fix this bug, the developer simply added proper handling to this exception. All right, now, by understanding this failure, we can make a few observations. First, we found that for this failure to happen, you need multiple input events. You need first, there's a load balancing event, and you need a node to crash. And in fact, among our randomly sampled failures, we found a vast majority of them require multiple events. Then the implication for testing is that a single event is not going to allow you to take down Google or any of the cluster. You need to come up with a combination of multiple events. And also that to make it complicated, a lot of these events will only occur on long-running systems, such as this load balancing event. All right. And in addition, the order of the events matters. Okay, for example, in this example, if we switch the order of these two events, the failure simply won't occur. So this indicates that as a tester, not only you need to come up with the right combination, but also the permutation. Okay. And in addition, we found not all the failures, they're deterministic, which means that it's not that you come up with the right sequence of the event, the failure is guaranteed to manifest. So actually, a quarter of them, they're non-deterministic, which means that even if you come up with the right sequence of events, you may or may not see the failure. And in fact, this failure is one of the examples. That in this case, the second event where the node crashes, it has to occur after the master has deleted the zookeeper node. And if this event has occurred slightly earlier, before the master deleted the zookeeper node, this failure will not manifest. Okay. Now, all these findings suggest actually it's quite complex for these failures to occur. And this is actually not surprising, because these systems indeed undergo through thorough testing. For example, for Hadoop, every patch you check in, you have to accompany it with some unit test. And every check-in, they use a lot of static checkers, and they have their own fault injection tools. And also, these failures are designed to tolerate component failures. For example, all the systems we study, they have this failover mechanism so that one master failure will not take down the entire cluster. Then the natural question is why those catastrophic failures still occur. So next, let's zoom into this catastrophic failure, where the failure will affect all or a majority of the users. So if we break down the life cycle of these catastrophic failures, we found that first, almost all of them are caused by bugs in the error handling code. Okay, so in these cases, once the fault is triggered, almost all of them will manifest into explicit error, but they are just not properly handled and eventually lead to a catastrophic failure. Now, this number might seem surprising, but it's actually quite intuitive as an afterthought, because these systems are designed to tolerate these failures. So those error handling code are exactly the last line of defense. And if that goes wrong, then you don't know what will happen. But if we further break down these bugs in the error handling code, we can see that over 1/3 of them is caused by trivial mistake. So for these bugs in the error handling code, you do not need any system-specific knowledge to detect them. So for example, one of the patterns is the error is simply ignored, not handled. Okay? And in fact, this trivial mistake have caused 1/4 of the catastrophic failures we studied. All right. And another pattern we found is we call abort in overcatch. Okay? So in these cases, the error handling code will abort the system. But these error handling code are overcatch, where more than one exception will fall through that error handling code. So for example, this is an example that you have a cache block that is an overcatch, where you have more than one exception that can fall into this, and you abort the system. And in all these cases, actually the abort is only the intended action for one of the exceptions. But it will accidentally take down your cluster for the other exceptions because it's an overcatch. Right? Note that I'm not saying that defensively aborting your system when you don't know how to handle the error is a bad practice. But I'm just saying that when you are going to abort your system, make sure your cache block or error handling block is precise. Don't catch an overly general exception and then abort your system, because very likely it's going to be an overcatch, and some unexpected exception will take down your system. Okay. And the last pattern is simply there's a to-do comment in your error handling block, such as this one. All right? So again, this is a user-reported failure to Hadoop MapReduce. Okay? This angry user says that, okay, so MapReduce job hangs when there's a rare resource manager restart occurred. So he had to SSH into every single node in his 4,000 node cluster to kill the job. Okay? After developers diagnosed the failure, the root cause is just this simple code snippet. All right? So the error simply is not handled, and there's a log being printed, and there's a to-do comment. So the proper fix is just add error handling to this block and remove that to-do comment. Now, in addition to these trivial mistakes, we found another almost 1/4 of the bugs in the error handling code are easily detectable. Right? By that, we mean that the error handling logic is completely wrong. Right? Any code, any tools that, as long as you trigger that error handling block, you will see the bug, you will see the failure, and also it could be caught by code review. Okay. So, for example, if you remember the previous HBase example, belong to one of this case. All right? In this case, the bug is in the error handling code, and it's simply completely wrong. So any test case that can trigger this code block, you will see the failure. Right? Now, for the remaining cases, indeed, they are pretty complicated. You require very detailed understanding of your system and very complicated analysis. But over half of the failures are either trivial mistakes or they are easily detectable. So they could have been prevented. Okay, now you might wonder that, okay, these are open source software. How about those proprietary software? Okay, so clearly not every failures in those closed source systems is publicly visible to us, but for the most serious ones, that usually they have a detailed postmortem. So for example, there was an outage for Facebook back in 2010 that today I think up to this date is still the worst failure in Facebook. So the Facebook was down for 2.5 hours, 2.5 hours. And the cause was simply error handling, incorrect error handling for a configuration error. Right? And for the previous, Amazon AWS failure, I previously mentioned, and indeed, it was also caused by an error handling code. Right? So the root cause was that there was a misconfiguration. that the administrators accidentally routed all the production traffic to a secondary network, which is not intended to handle production traffic. However, so as a consequence, a lot of requests start to time out. But the handling of such timeout requests, instead of to aggressively back off sending your network traffic, each node will actually aggressively send a lot of lookup requests. So it will actually increase the traffic, so essentially take down the entire AWS. Okay. So for all these failures, remember that the actual fault is complicated, and then actually it's not only error handling code. But if there's no such bugs in the error handling code, they won't manifest into a catastrophic failure. Right. So now, based on these observations, we built an embarrassingly simple tool called Aspirator. It's a static analysis tool. It exactly detects the 3 patterns we have observed in the trivial mistake. That for every single cache block, we'll first check whether it's empty or not, okay? Or whether it will abort the system on an exception over cache, or whether it contains comments like to do or fix me. All right? So we do have some false positive suppression techniques. If you're interested, you can read our paper. And clearly, if this tool is used and the detected bug has been fixed, over 1/3 of the failures we studied, a catastrophic failure we studied, could have been avoided. But we further applied this tool on the latest version of some distributed system, and we see whether we can find new bugs. And this is our result. All right? We applied the tool on 9 distributed systems. 4 of them is already included in our study, so we call this set training set. And there are 5 new ones that it was not included in our study. We call them testing set. And here's the result. So you can see that first, Aspirator reported 500 bugs. And also that for every single system, Aspirator reported at least 1 new bug. All right? So actually, if you have a large Java code base, I recommend you can run Aspirator on that code base. The result will surprise you. And clearly, a lot of these bugs will cause catastrophic failures. So for example, one of the commonly observed bug pattern is that so when they are trying to release a lock, and this lock release throws an exception, and that exception is simply ignored, you can result in a deadlock. And this pattern actually is observed in multiple systems multiple times. And some of these bugs could result in data loss. For example, this is a code snippet in HDFS. Okay, so when during the journal recovery process, which is already handling some errors or inconsistency on your file system, and if it throws an exception, and if it's ignored, it could lead to inconsistent file system. And finally, a lot of these bugs could result in cluster crash. For example, all the bugs that are detected by this aborting overcache check could result in crash. And we reported 171 bugs to the developers, and we received mixed feedbacks. Okay, a lot of the developers welcomed our patch and said a lot of good things about our patch. So for example, no one would have looked at this hidden feature, and ignoring the exception is bad precisely for this reason. Okay, and another developer, I believe, is from CloudStack. He said, I really want to fix issues in this line because I really want us to use exceptions properly and never ignore them. Okay. But also, there are some developers told us, I fail to see the reason to handle every exception, and they rejected our patch. Okay. And we think exactly this kind of attitude are the reasons why there are such trivial mistakes in the error handling code. Okay. The natural question is why? Why do developers ignore error handling? Okay, here are some of our observations. So sometimes the developers wishfully think that the error will never happen, so they just ignore it. And this is an example, all right? And, but we still argue this is a dangerous practice because later code evolution might enable the error, so you ignore it. And sometimes this judgment can be simply wrong, right? So in this example, the developer think that it is impossible for this time range constructor to throw an exception, so they ignore it and put a comment, will never happen. But if you look at the constructor of this time range, it could have thrown the exception in the case of an integer overflow. Okay, so this is immediately fixed by the developers after we report it. And also that sometimes the error handling is just difficult, okay? Especially for those errors that are thrown by the third-party library where we have no idea how to handle it. So for example, in this case, this exception, no transition exception, was simply ignored. And in the comment, the developers complained that God is not helping him to understand it. Right? And finally, it's just unfortunate that feature development is always prioritized, so that when the deadline is there, people tend to ignore the error handling. But those are exactly the reasons why you could have a catastrophic failure in your production system. And in the paper, we have talked about some other findings, and if you're interested, you can take a look. So for example, we also found that although these failures typically occur on a large cluster, but to replicate it, usually you don't need more than 3 nodes. Okay. Now, I'm not saying that it's useless to have a large cluster for testing, because in the end, the testing is just a probability game. Okay, the larger the cluster you have, there's more chances that you can hit those failures. But if you have more guided testing, such as you are testing explicitly for every error handling block, you might not need such a large cluster. And also we found that for this system, actually they have a very strong unit test framework, that all these failures could have been reproduced offline through a simple unit test. So for example, for HDFS, so in their unit test, they could just fire up a thread to simulate the execution of each node, right? And also that the failure triggering events are typically in the system logs. So when you have a failure, by looking at the logs, you could know how to reproduce it. And although we made the observation that a quarter of the failures that are non-deterministic, but the majority of them actually still could be deterministically reproduced. By that, I mean that the timing requirement in these failures are actually usually between some internal function calls. So that if you unit test, if you use unit test, you could still try to control the order of these function calls, so you can still deterministically reproduce them. And so our work was published actually last year in October. So since then, we have seen a lot of reactions from the developers. So for example, we have been featured on the front page of Hacker News multiple times, and there are tons of blogs written about our work. And today I checked, there's even a book called 50 Quick Ideas to Improve Your Test that they discuss our idea. So this is, I'm quoting one of the developers written in his blog to say, read this paper and perhaps put it on a 90-day reading rotation. Okay. And there are hundreds of Twitter discussions. So here are just a few examples. And actually this week I was told that in the Cassandra summit, in the keynote, so they were discussing our result. And if you remember in my previous slide, you might see that HBase has the most number of bugs. But actually, HBase developers really took our paper really seriously. They created this ticket just to discuss all the findings from our paper, and they created a lot of subtasks, okay, to fix all the issues that are mentioned in our paper. And they actually will use Aspirator as their compile time checker. So we developed a customized Aspirator version for them. It's based on error-prone, so which is integrated in Java C. So every time when you compile the code, we'll basically issue those warnings. Okay, so in summary, what I told you basically is, again, these 3 findings. We found that failures are the result of complex sequence of events. But for the most catastrophic ones, they're almost entirely caused by incorrect error handling. And many of them are caused by a small set of trivial bug patterns. Okay? And we further designed a tool called Aspirator that could detect many of these bugs. And that's pretty much of my talk. So I want to end by showing some of the code comments in the error handling block that are detected by Aspirator. All right? So basically, these comments appear in the code block belong to one of those 3 patterns I mentioned. All right? I think we can actually write a book just about these comments. And with that, I'm happy to take any questions. Yeah.
I just want to say this is really awesome.
Thank you. Thank you. Yeah. But to be honest, I mean, sure, we develop a tool, but I think the bigger issue is developer education. For example, a lot of people, they just simply have this philosophy, why do I care? Sure, I mean, if you're, especially for new hires, right? If you're students, graduate students, you're always go with the quick and dirty, you're always under deadline. But once you're writing code that is going to be used in production, these error handling code are exactly the ones that you should really care more about. Okay? Because it's very hard for testing to expose those the bugs in the error handling code, so they might escape testing, but once you throw it in the wild, it will be hit eventually. Yes?
How hard would this be able to apply?
Good question. So really the complexity or the challenge to apply to other language is to know where is the error handling code. In Java, we have benefit from that exception is a language support, so that we know every catch block is error handling code. But in C, we don't know. Right? There are some heuristic. For example, every system call return, non-zero system call return is error handling, or every fall through to switch statement could be error handling. But you could think about a lot of these error conditions are just customized. So then the challenge is really where do we know that it's an error handling code block? But once you know that, the check is trivial. Yeah. Any other questions? All right. Thank you, guys.